All right, we're going to talk about laminar fluid drag, and really specifically on spheres. So, other shapes will also have air resistance or drag if you move it through a fluid, but the formulas are more complicated, so we're going to specifically stick with spheres. So the idea here is if we have a sphere that's moving through a fluid, right? This could be moving through the air, or it could be moving through water, or it could be moving through honey. But if it's moving through a fluid, there's going to be a resistance force. There's going to be, this could be, you could call this air resistance, or if it's moving through water, you could call it water resistance, but the fluid's going to try to slow it down. And this could happen in one of two ways. You could either have the fluid, right? The fluid's got to go around the object, right? And if the object is moving slowly, this is going to have what's called laminar flow. And if it's nice laminar flow, then we have a nice easy formula we can use to predict how strong the resistance is. However, if the sphere is moving too fast, we will get turbulent flow. And turbulent flow, you have the fluid coming around, and then it starts making horrible, chaotic flow behind the sphere, and that would be turbulent flow. And if we have turbulent flow, then our formulas that we're using don't work. So again, we're going to be using Reynolds number. So Reynolds number is equal to the density of the fluid that we're flowing through times the velocity of the sphere times the diameter of the sphere divided by the viscosity of the fluid. And again, if this number is less than about 2300, we should expect laminar flow. If it's more than about 2300, we expect a turbulent flow. And if the flow is laminar, then we can find out that the drag force, the force that's trying to slow down the ball, would be equal to a nice simple formula. It's equal to 6 pi times the radius of the ball times the viscosity of the fluid times the velocity of the ball. And what I want you to see here is that the drag force gets bigger the faster the object is moving, and I hope that makes sense. The faster the object is moving, the more air resistance we're going to have, the more fluid resistance we're going to have. So these are the two formulas that we'll end up using when dealing with calculating how strong a fluid resistance force is when we have a sphere moving through a fluid. So I'm going to go ahead and do an example. And the example I want to do is to imagine that we have a ball that's underwater. And I'm going to make this a lacrosse ball. Okay, and let me go ahead and look up some numbers. Okay, so we're going to say that the density of this lacrosse ball is about 930 kilograms per meter cubed. And so that means it floats, right? Because it's less than, so that's the ball. And the density of the water is 1,000 kilograms per meter cubed. So a lacrosse ball has a diameter of about 63 millimeters. So that's 0.063 meters. That's about 2.5 inches. Okay, so if you know what a lacrosse ball is, it's about the same size as a tennis ball, but it's made of solid rubber, so it just barely floats in water. In fact, some lacrosse balls sink in water, but I've decided to make my lacrosse ball out of a relatively lightweight rubber so that it will float in water, but just barely. Okay? And actually, what I want to find is how fast will this ball be moving up through the water? How fast will it be moving when I let go? So when I let go, it's going to start moving upward, and very quickly it's going to reach terminal velocity. That is, it's going to reach a speed where it just keeps going at constant speed. And I want to find out what that speed is. So I guess one other thing I need is the viscosity of water. And water has a viscosity very close to 1. Okay. And that's if it's at room temperature. If you get water really cold, the viscosity goes up. If you get water hot, the viscosity goes down. But at room temperature, the viscosity of water is very close to 1. Okay, so let's see if we can figure out how fast the ball will be moving through the water. And the way we're going to do that is we're going to set up a free body diagram. And we have got 3 forces acting on this lacrosse ball. First force, really obvious, is going to be gravity. Okay. And then another force, which I hope is pretty obvious from last week, is going to be the buoyant force. That is, the water all around the ball is going to be pushing up on the ball. And since this ball is moving upward, it's also going to have a drag force, like, a fluid resistance. Think of it like air resistance, except for water. The ball's moving upward, and so that resistance is going to try to slow it down. So I'm going to put that here. We call that F sub S. That is the slowing force from moving through a fluid. And remember, this only works if we have laminar flow. So it's got to be this nice, smooth flow of fluid around the ball. And if we have this nice, smooth flow of fluid around the ball, we get this backwards force that's equal to 6 pi r eta v. Okay, now those 3 forces have to add up to mass times acceleration. But the ball is moving at constant speed. It's not speeding up or slowing down. It has reached a constant speed, so the acceleration is going to be 0. So what does that mean? That means that the buoyant force minus the slowing force from moving through the fluid minus gravity should equal 0, which means that the density of the water times the volume of the ball times g minus our formula for the Fs is 6 pi radius of the ball, viscosity of the water times the velocity of the ball, and the force of gravity is going to be minus the mass of the ball times g, and those 3 forces need to add up to 0. So the mass of the ball is going to be equal to the density of the ball times the volume of the ball. So we can plug that in. And so I'm going to solve this for velocity. So the first thing I'm going to do is add that 6 pi term to both sides of the equation. So I get the density of water times the volume of the ball times g minus the density of the ball times the volume of the ball times g is equal to 6 pi radius of the ball times the viscosity of the water times velocity. So now I need to divide both sides by 6 pi r eta to get velocity. So my velocity is equal to, and I'm going to combine these two terms. It's equal to the density of water minus the density of the ball times the volume of the ball, and the volume of a sphere is 4/3 pi r cubed times g divided by 6 pi r eta. So a couple things happen. That pi cancels with that pi. I can cancel, so this, one of those, that r cancels with one of these r's, so that becomes r squared. So this simplifies a little bit. V is equal to the density of the water minus the density of the ball times r squared times g, and then that's going to leave me with a 2 in the numerator and a 9 in the denominator. And what I did there is I took the 4/3 over 6, and that became 4/18, which became 2/9. So this is 4/3 divided by 6 is equal to 4/18 is equal to 2/9, and so that's where my 2/9 came from. So that formula is not just for anything, that's specifically for this ball traveling through water. So we had a buoyant force, we had a drag force, we had a gravity force. Okay, but this gives us our velocity. And so let's see what we get. So my velocity is equal to 2 times the difference in the density. That's 1,000 minus 930, so that's 70, times r squared, so that's 0.063 squared, times g, which is 9.81, divided by 9 times 1.0. Okay, so let's see what we get. 2 times 70, 2 times 70 times 0.063 squared times 9.81 divided by 9 times 1 is equal to 0.606 meters per second, or really to two significant digits, that would be 6.1 meters per second, or 0.61 meters per second, so a little bit less than a meter per second. Okay, so now I'd like to know what the Reynolds number is. And the reason I want to know what the Reynolds number is because this is only valid if the Reynolds number is low. If the Reynolds number is high, then that means we'll have turbulent flow and this equation won't really work. So I need to check to see if this is really a valid answer by checking the Reynolds number. So to find the Reynolds number, we're going to need the density of the fluid times the velocity times the diameter divided by the viscosity of the fluid. So this is 1,000 times 0.606 times the diameter of the ball, oh crap. Oh crap. I did this wrong. I needed to put in the radius of the ball, and I put in the diameter. So this is actually 0.0315. Oh dear. All right, so 2 times 70 times 0.0315 squared times 9.81 divided by 9 is actually 0.151 meters per second. Okay, so it's actually going slower than we thought. Sorry about that. Okay, but to calculate the Reynolds number, I do need the diameter, 0.063, divided by the viscosity, which is equal to... Son of a bitch. I said the viscosity was 1, but that's not right. Viscosity is 1 times 10 to the minus 3. Son of a motherless goat. I did everything wrong in this problem. That's going to give us a really interesting answer. That can't be right, though. Two times 70 times 0.0315 squared times 9.81 divided by 9 and divided by 0.001. 151. That's exciting. 151 meters per second. Pretty sure that's going to be a BS answer. It just seems unreasonable, right? You put a ball in the water, it does not go up at 151 meters per second. So let's see what the Reynolds number is. 1,000 times 151 times 0.063 divided by 0.001. Oh yeah, the Reynolds number here is 9,530,000. So do you think that might be bigger than 2,300? I think so. Which means that if the ball was really traveling 151 meters per second, we would have massively turbulent flow, which means that this result is bullshit because you cannot get a result. You cannot trust the result. This answer assumes that we have laminar flow. But this result shows that we wouldn't have laminar flow. And so that means that the answer can't be trusted. Boy, I feel like I might have made a mistake or two on this problem. I feel so badly for that. I'll be careful when I'm giving you problems to make sure I give you the right viscosity. In the table I was looking up, the units were different. So I forgot to convert units to Pascal seconds instead of millipascal seconds. And I made the same mistake in the previous problem when I was doing air going through the pipe. But that only really mattered for B. Interesting. Well, so, or maybe I didn't make a mistake on that one. Maybe I remembered to convert the units on that one. Yeah, I remembered to convert the units on that one. So no mistakes on that problem. There was a mistake on this problem, but I fixed it. And I think this answer is now right. Anyway, I'll be sure to give you the right viscosity and the right units when you're doing homework problems. But you do need to remember to convert between diameter and radius when needed. If your problem says radius, make sure you plug in the radius. If the equation uses diameter, make sure you plug in the diameter. Okay, well, I hope this was instructive. You do have a problem somewhat similar to this one, where we have an object moving through a fluid and there are three forces acting on the object: a buoyant force, a drag force, and gravity force. Except your problem, the object is falling through the fluid. So that's going to affect which direction one of those forces points. So it's going to slightly change the problem. Hopefully you can work that out, and I will